Today's topic is ratio and root test for absolute convergence of series. So we'll first start talking about ratio test. Ratio test is let an be a series with non-zero terms. The an converges absolutely if limit n goes to infinity, absolute value of an plus 1 over an is less than 1. If that limit of an plus 1 over an, absolute value of it, as n goes to infinity, turns out to be less than 1, then the series converges absolutely. If the limit is greater than 1 or it's equal to infinity, then the series diverges. If the limit turns out to be equal to 1, then ratio test doesn't tell us anything. We will have to look at some other test to figure out about convergence and divergence of the series. Now, when to use the ratio test? When we have exponential functions, factorials, or n to the power n. When not to use ratio test, when we have rational functions. So let's see some examples of ratio test in use. Determine the convergence or divergence of the following series. So we'll start with the first one, and this is my an. An is 2 to the power n over n factorial. An plus 1 would be 2 to the n plus 1 over n plus 1 factorial. Okay, so I'm going to do limit n goes to infinity. Limit n goes to infinity. Limit n goes to infinity, 2 to the power n plus 1 over n plus 1 factorial divided by, so we're doing, let me first write down, limit n goes to infinity, an plus 1 over an. So we're trying to figure this limit out. So limit n goes to infinity, an plus 1 is 2n plus 1 over n plus 1 factorial, and divided by 2 to the power n over n factorial. Now all we have to do is just a little bit simplification, cleaning up, and see where does it take me. Limit n goes to infinity, 2 to the power n plus 1, it can be written as 2 to the power n times 2. N plus 1 factorial can be written as n factorial times n plus 1. We can break this. For example, 10 factorial, we can write it 9 times 9 factorial times 10, or 10 times 9 factorial. It's the same thing. So that's exactly what I'm doing here. I'm breaking the n plus 1 factorial into n factorial times n plus 1. And when we divide the fractions, we change the division into multiplication and flip the second fraction. So n factorial over 2 to the power n. Now we would be able to cancel a lot of terms here. N factorial is gone, and we're left with 2 over n plus 1. So where does this limit go for 2 over n plus 1? We have limit n goes to infinity, 2 over n plus 1. This limit goes to 0. So if this limit goes to 0, and we said if our limit turns out to be less than 1, then we have absolute convergence. Absolute convergence. Absolute convergence if the limit turns out to be less than 1, and 0 is less than 1. 0 is less than 1. So we do have absolute convergence in this case. Let's check out another example. So I'm going to make some room for the second problem. Part B. Here I'm given an is n squared 2 to the power n plus 1 over 3 to the power n, and an plus 1 is n plus 1 to the second power 2 to the power n plus 1 over 3 to the power n plus 1. And I'm going to go ahead and do the limit n goes to infinity, an plus 1 over an. So I'm going to skip the middle step where I'm going to write the two fractions with the division sign in the middle. I'm going to write multiplication sign in the middle and flip the bottom fraction. Limit n goes to infinity, n plus 1 squared 2n plus 2 over 3n plus 1 times, flip the second fraction, n squared 2 to the power n plus 1. Okay, so now just a little simplification and see all the terms that I can cancel, maybe rewriting some of the terms. I'm going to leave n plus 1 squared as it is, 2 to the power n plus 2. Small eraser. N plus 1 squared, 2 to the power n plus 1 times 2. That's the same thing as 2 to the power n plus 2. And we have 3 to the power n in the numerator. The denominator, I have 3 to the power n plus 1. I'm going to write it as 3 to the power n times 3. And then I have n squared, 2 to the power n plus 1. Let's go ahead and cancel all the terms we can cancel. 2 to the power n plus 1 is gone. 3 to the power n is gone. And we are left with limit n goes to infinity. I can pull the 2 out, 2/3 out. We're left with n plus 1 squared over n squared. N plus 1 squared over n squared. Now where does this limit go? What does this turn out to be when n goes to infinity? This is going to equal 1 because we have the same degree in the numerator and denominator. 2/3 times 1 is equal to 2/3. So that tells me 2/3 is less than 1. Again, I do have absolute convergence. Absolute convergence here. Absolute convergence. So if my limit turns out to be less than 1, I have absolute convergence. If my limit is anything greater than 1, then I have a divergence. If my limit is equal to 1, when I do the ratio test, I'm not able to say anything based on the ratio test. I have to think about another test. Let's look at a couple more examples of ratio test. So again, limit n goes to infinity, absolute value of a n plus 1 over a n, which is limit n goes to infinity, absolute value of a n plus 1, n plus 1 to the power n plus 1 over n plus 1 factorial times n factorial over n to the power n. Okay, so for simplifying over here, we can go ahead and limit n goes to infinity, n plus 1 to the nth power times n plus 1 times n factorial over n factorial times n plus 1 n to the nth power. Okay, now I can get rid of n plus 1 and n plus 1 here, and I can also get rid of n factorial. So we're left with limit n goes to infinity, n plus 1 to the nth power, n to the nth power. So where does this limit go? Let's see. This limit matches, we can express it slightly differently. We can call it, this can be written as limit n goes to infinity, n plus 1 over n to the power n. Now this is the definition of e. 1 plus 1 over n. If you recall, the definition of e is 1 plus 1 over n to the power n. That's what the number e equals as n goes to infinity. So limit n goes to infinity. That's the definition of e. So that means this limit goes to e. E is the absolute value of e is approximately 2.7, which is greater than 1. So that means this series diverges. This series diverges. Let's check out next example. We have negative 1 to the nth power square root of n over n plus 1. Let's see, we are going to use the ratio test here again. Ratio test says, go ahead and do the limit n goes to infinity, a n plus 1 over a n, absolute value of that. So limit n goes to infinity, absolute value of, it's an alternating series, negative 1 to the power. So let's write the a n term here because we have alternating series. We might have to switch some things. A n is negative 1 to the nth power square root of n over n plus 1. A n plus 1 would be negative 1 to the n plus first power square root of n plus 1 over n plus 2. So now I'm ready to go ahead and take the limit. Limit n goes to infinity, a n plus 1, which is negative 1 to the power n plus 1 square root of n plus 1 over n plus 2 times n plus 1 over negative 1 to the power n square root of n. Let's see all the terms I can simplify or I can cancel here. Limit n goes to infinity. I might have to rewrite negative 1 to the power n times negative 1. I'm going to write that. Then I have square root of n plus 1. In the denominator, I have n plus 2. I can write it. I cannot write it as, I will just leave it as n plus 2. And then I have n plus 1 over negative 1 to the power n square root of n. Okay, so a little bit cleaning up, simplification, combining or writing, rewriting. I can get rid of negative 1 to the power n, so that piece is gone. Now in my absolute value sign, I can write it as n plus 1 over n times n plus 1 over n plus 2. I can just kind of separate the two. I do have a negative 1 somewhere in the absolute value sign as well, but I'm going to get rid of that because I do have absolute value sign. The negative can disappear in there, so I'm not going to bother about that. When n goes to infinity, where does this limit go? Where does this limit go when n goes to infinity? Both of these limits go to 1 because they are kind of same degree in the numerator and denominator, so the limit turns out to be equal to 1, so ratio test is inconclusive. If the limit turns out to be equal to 1, then we cannot say anything based on the ratio test. Ratio test is inconclusive. Okay, let's see. Now we're going to look at the root test. Root test is also used to determine absolute convergence. It's it's kind of similar to the root ratio test, but instead of taking the ratio here, we take the root. So this works very well with the series involving nth power. So when you have n raised to the nth power, we can use the ratio test. I'm sorry, we can use the root test. We can also use the ratio test in those cases, but it's easier to use the root test. So here, if an converges absolutely, if limit n goes to infinity, absolute value of an nth root is less than 1. This series diverges if limit n goes to infinity, nth root of absolute value of an is greater than 1, or the limit is equal to infinity. The root test is inconclusive if the limit turns out to be equal to 1. Okay, let's see examples of the root test. Here is the first example. Summation n is equal to 1 to infinity e to the power 2n over n to the power n. Okay, so I'm going to go ahead and write the nth root here. So limit, I'm going to apply the root test. Limit n goes to infinity, nth root of the an, which is e to the power 2n, nth root of e to the power 2n over n to the power n. Limit n goes to infinity. That would be, I'm going to get rid of the radical sign, but instead write it as the power 1 over n. E to the power 2n would be, exponent would become 1 over n, and n to the power n, 1 over n. See, where does this limit go? Limit n goes to infinity. N and n will cancel, so e squared in the numerator, and we have n in the denominator. E squared in the numerator and n in the denominator. When n goes to infinity, this limit goes to 0, which is less than 1. So we do have absolute convergence in this case. Absolute convergence. Okay. Now we're going to look at number 2, where we have n equals 0 to infinity, and we're given the series. We're going to take the nth root. As you can see, if we had tried the ratio test here, it would have been very much complicated. Root test is a lot easier to apply in this case. So let's see. Root test is limit n goes to infinity, nth root of absolute value of 5n minus 3n to the third over 7n to the third plus 2 raised to the nth power. Okay, now I'm going to write the nth radical as an exponent. So I have 5n minus 3n to the third over 7n to the third plus 2 to the nth power and 1 over n. So now n times 1 over n will cancel. Limit n goes to infinity, and I'm left with 5n minus 3n to the third over 7n to the third plus 2. These, we know, they are the same. This is like a horizontal asymptote for a function. Limit at infinity is like what y value do we approach when x gets really large? Because we have both numerator and denominator the same degree, it's going to be leading coefficient of numerator divided by leading coefficient of denominator. Leading coefficient would be -3 for numerator, because we would write it in the standard form with the higher exponent first and then lower and the lower. Now this is less than 1. So if my limit turns out to be less than 1, then I do have absolute convergence. I have absolute convergence. And that's all for ratio and root test.